This video is about OFDM modeling for wireless communications. Previously, we recorded video to demonstrate complex wireless system using emulation and modeling. You can find them at the links on this slide. The focus for this video is about orthogonal frequency division multiplexing. For wireless applications, OFDM has application in both in the air and under the water, both of which has a lot of interference due to natural or man-made. On the left-hand side here, you can see example of wireless communication in the air and on the ground. And there are problems in those type of communication due to cloud, fog, rain, or vegetation, or the distance between the transmitter and the receiver, or the transmitter power or the receiver sensitivity, or the speed of traveling, which cause Doppler effect, or the frequency of which the signal is being transmitted or receiving. And man-made things like jamming can cause problems. And also for secure communication, you want to avoid people from intercepting your signal or detecting the signals. On the right-hand side, you can see diagrams for underwater network communications. Under the water, we have different type of issues. When we send signals out, it can reflect off of the surface of the water or from the bottom of the ocean. In addition, there are animals in the ocean that can generate noise and things that can cause additional problems. So why OFDM? OFDM uses multiple subcarrier frequencies to communicate, unlike conventional methods, which use single carrier. So a major advantage for OFDM is it's able to cope with severe channel conditions and better signal-to-noise ratio. It has concept called guard intervals to protect against intersymbol interference. And it can support recombining of signals from multiple transmit sources. It's a sort of beamforming, if you will, so you can get stronger signal, less interference than traditional single carrier method. It offers more security. Since your data is being spread out across multiple spectrums, it's more difficult to intercept or detect. It supports forward error corrections, time frequency interleaving, which overcome errors, multipath propagation, Doppler effect due to traveling speed, and interleaving itself has additional security features. For implementations, OFDM can be implemented in hardware acceleration using technology such as FPGA, a field programmable gate array, or software like C code running on CPU. Software is typically used for lower bit rate. Higher bit rate requires hardware accelerations, or if you want to implement advanced concepts such as advanced error corrections, then hardware acceleration is recommended. The following demo, we will show hardware acceleration using Verilog code.
In this demo, we will see the operation of OFDM transceiver. It is currently implemented in Verilog simulation environment. The test bench consists of OFDM transmitter, receiver, and the simulation of channel. In this demo, we will be using ideal channel without any noise effects. The test bench reads the sequence of bit symbols from an input file and sends them through the transmitter. Since we are using QPSK modulation scheme, each bit symbol consists of 2 bits and can take values from 0, 1, 2 and 3. OFDM time domain waveform is generated by the transmitter and it is then sent through the channel to the receiver. Receiver then converts the time domain waveform back into the frequency domain symbol and we are able to retrieve the original bit sequence at the end. Now we will take a look at the block diagram of the OFDM transceiver. The important blocks in the transmitter are the modulator and the inverse fast Fourier transform IP core. On the receiver side, we have synchronization module which detects the start of the frames, the fast Fourier transform which is another IP core, and the demodulation module. In this illustration, we will be using following design parameters. As mentioned before, we are using QPSK modulation scheme. The constellation can be seen on the right. We are currently using IEEE 802.16 standard, which consists of 192 data subcarriers to be used in OFDM. So we can transmit 192 bit symbols in each OFDM symbol. Apart from that, it also consists of 8 pilot carriers and 28 guard symbols on each side of the frequency spectrum. The frame format in the frequency domain is shown below. Now we are assuming the signal bandwidth to be 10 MHz. So that gives us the symbol time for OFDM to be 25.6 microseconds. Now in this demo, we will be sending 2 OFDM data symbols per frame. They are accompanied by 2 preamble symbols which are then used by the receiver for the synchronization. The FFT used is made of 256-point FFT, and we are also attaching each symbol with cyclic prefix of length 32 points to avoid the inter-symbol interference. Now we will switch to the simulation environment for the demo. Now we are in the Verilog simulation environment, and you can see on the left the design hierarchy for the transceiver. You can see different code blocks for the transmitter as well as the receiver as shown in the previous block diagram. Now in the project top directory, you can see the input data file which consists of bit sequence for the different bit symbols. Now we'll be sending these bit sequence through the transmitter and then retrieving it back via the OFDM receiver. Once the simulation is complete, the test bench will generate the output file which consists of retrieved bit symbols, and we will be able to compare the information in both files. Now let's run the simulation. So we are currently sending 2 OFDM frames through the transmitter. They will travel through the channel and then retrieved by the receiver. The simulation is complete. So in this wave, you can see the transmitted frame. This is the first frame and this is the second. This is the transmitted waveform at the channel interface. Once the receiver receives this sequence, it then performs synchronization and equalization operations. And in the end, you can see we finally get the received bit sequence. Now let's take a look at the project directory. As you can see, we have generated the data out symbols, which are the symbols retrieved by the receiver. Now if you compare the information in both files, they are identical. So we are able to receive transmitted bit symbols with complete accuracy at the receiver end. Now we will take a look at the actual OFDM waveform generated by the transmitter. As you can see, the test bench also generates 2 additional files consisting of real and imaginary parts of a time domain complex signal generated by the transmitter. Now we can view this waveform using another tool. This is the OFDM waveform in the time domain. This waveform consists of a single OFDM frame which consists of two preamble symbols which are highlighted in blue. Now it also consists of two OFDM symbols which are highlighted in red. Now both preamble and OFDM symbols are separated by the cyclic prefix which is highlighted in green. The first waveform represents the real part of the OFDM transmission wave, and the second wave represents the imaginary part of that complex time domain sequence. With this, we conclude this demo. Thank you for watching.